Hey, welcome back. We're looking at centripetal forces, part two. If you haven't checked out the first centripetal force video, I highly suggest you do that. It covers what an acceleration or a centripetal acceleration is, what a centripetal force is, and how we can start thinking about some of it. So what we're going to do here is we're going to start analyzing some more of the problems and how we can start looking at that the sum of the forces to make a centripetal force equals this mv squared over r, and how we can set this up and how we can start thinking about them from a problem standpoint. Well, if we take a look at what we have here, when we start thinking about centripetal forces acting on an object, they're really a sum of forces to make a centripetal force. And if we, think about the foxtail, which we've been talking about, as I swing it around, let's think about it at the very top of its position and the very bottom of it as we're looping it like that in a vertical arc. Okay? If we're looping this in a vertical arc, then, and here I'll kind of draw the arc like that, and here's our very bright foxtail. Then when this foxtail gets to the top of the arc, there are two things that we need to concern ourselves with in terms of forces acting on the foxtail. Remember, weight is always acting on an object. This foxtail has some mass associated with it, and therefore it has to have a weight associated with it. And that weight is always acting down or inwards towards the center of the earth. So that is the weight of the foxtail right there. Well, we also know whenever this is being spun around and it gets to the top that there is some tension in this nylon cord pulling towards the center of the circle. So we also have here pulling, once again, down a tension. So both the tension and the weight here are pulling down, but what we're really going to say here is they're pulling inward towards the center of our circle, because that's a poorly drawn circle and it's much better over here. Okay? But they're pulling inward towards the center of the circle. If our foxtail is at the bottom, though, things change slightly. Here's our foxtail. The weight still has to pull down. It can't do anything but. It's got to go towards the center of our Earth, our planet. But when the foxtail's at the bottom here, there's still a tension pulling up towards the center of that circle. And that means the tension in this case is actually acting up. So we still have a tension, we still have a weight here, but they've now switched directions of the tension so that our tension is acting towards the center of our circle and the weight is pointing to the outside of our circle here. What we're going to do is we are always going to identify the positive direction to be towards the center of the circle. So this tension and this weight on the left-hand side there, they are both positive values because they're going towards the center of the circle. Over on our right-hand side when we're at the bottom, our tension is positive because it's moving towards the center, but our weight is negative because it's leaving the circle there. And that's going to be an important idea for whenever we have to sum these forces together. Some might be positive, some might be negative, and that's fine. If we have a hill and valley, it's the same idea. Maybe you're a car going over the top of a hill. Well, instead of a tension existing there, what's actually keeping you in the loop is a normal force. It's the ground pushing back up on you. And if we kind of look at the hill and valley, there is a weight pulling down, but the normal force is pushing you up. It's like the road pushing back on you. And if we look here, the weight is pulling down, but the normal force is pushing back up in towards the center of the valley. So this kind of scenario here, while they might look similar, up, up, down, down for the normal and weights respectively, here the normal's negative, the weight's positive. On the other one, the normal's positive and the weight is negative. So it's a very similar idea, but keeping track of those plus and minus signs is important for what we're about to do. And we're actually going to look at the hill and valley problem right now. So if you're in the class, if you're a resident of the region, you may be familiar with the Chick-fil-A. And if you've been driving along that kind of road next to Chick-fil-A and it kind of got those like bumps on it, you may have hit the gas pedal a little bit and woo! All of a sudden like felt like you were flying out of your car seat, almost like you were at Kennywood at the double dips on the Jackrabbit. There's a reason why your stomach all of a sudden feels like it's up in your throat whenever you kind of hit those bumps by that hill. And the reason is this idea of a centripetal force and the specific normal force here. Remember, your normal force is an apparent weight. Your normal force is what you feel, okay? Whenever you hop out of an airplane without a parachute for some reason, you don't have a normal force immediately acting on you. So you feel like you're in free fall. You feel terrified for a moment. It's not till like the air resistance pushes back on you where that normal force all of a sudden exists and you feel normal again. So the normal force is an apparent weight. It is what you actually feel. So if we're going along this Chick-fil-A road at a constant speed of 17 meters per second, and we encounter a dip in the road. So we have got a dip in the road here. We're not, having our stomach up in our throat, but we have a dip in the road, and a dip is like that. We're going to approximate this dip as a circular arc, despite the fact that I did not draw it as such. So we can imagine that there's like some center somewhere in the arc, and it has some radius here of 65 meters. We would like to solve for the apparent weight, the normal force, of an individual that has a mass of 80 kilograms, so 784 newtons, when the car is at the bottom of the dip. So what we have is our car will be at the bottom of the dip, and we're looking for the normal force, which means that we are going to be using that the sum of the forces equals m, and since we're moving in a circular arc here, v squared over r. So if we go ahead here and draw our forces acting on us here in the car, we have a weight acting down, and we have a normal, let's draw that in pink. We've got a normal acting up. Our normal going towards the center of the circle is going to be positive. The weight is going to be a negative quantity. So when we write out our sum of forces here, and this is so important because there's two of them, we're going to have a normal force, which was positive, plus a negative, so adding a negative is subtracting, so minus a weight, and this is going to equal an mv squared over r. Now, we're solving for the normal force here, so we're just going to leave that as n. And we happen to know our weight. We've got 80 kilograms of a mass, but we know our weight here is m times g, so 80 times 9.8 gives us 784. So we can say the normal minus 784 equals, and then here goes our mass, which is, in this case, 80 times v squared, which is 17, over r, which is 40? 65. 65. Whoops. Numbers, right? 65. And at this point, we can just go ahead and solve for n. I actually really quick want to just do this. I'm going to set this equation up without any of the numbers just to take a look at something real quick. If I set this up without any numbers, I'm just going to add the weight over to the other side. So this is going to become the normal equals mv squared over r plus the weight. And if we remember, weight is equal to mass times gravity. Well, if I look at this, I have a mass and a mass, and those masses are the same thing. It's the 80 kilograms of the person. So I'm actually going to pull that out. If I factor that out, I see that the normal equals a mass times the quantity of gravity plus v squared over r. I just flipped which order I added them in. What we actually see here is that you're going to feel heavier. The reason being is you have a normal or a traditional weight, mass times gravity, mg, but then you're adding the extra felt weight from going through that loop. And if you've been on a roller coaster and you're kind of at the bottom of a hill there, you kind of feel like you're being pushed back in your seat and you're being crushed. And that's why. It's because we have to add this extra v squared over r onto that normal force. And if we do this in this case, and also, by the way, writing it like this here over to the side, that's a lot easier mathematically than throwing in a bunch of numbers in the beginning. This is a little bit easier to solve through. If I solve for that, and I kind of want to rewrite this, this is going to be the 80 times 9.8 plus 17 squared over 65. So it's the same thing, just looks a little easier for us to solve. So 17 squared is 289, divided by 65 is 4.4, plus 9.8 is 14.2, times 80 gives us a new normal force equal to, let's round up, 1,140 newtons. And if we wanted to see like what would our mass be at that point, your mass would be like 116 kilograms. So you kind of increased your weight by 50%. So you feel a little bit heavier doing that through the turn. You feel like you're being pushed down more. You feel like you're being squashed. That is what's going on there. Now, if we were going over a rise of the same radius, and this is what you're encountering at our actual Chick-fil-A hill, when you're going over a rise like this, and here's your car, well, everything is pretty nearly the same, except our forces are in different directions. Now our normal's pointing out, our weight is pointing in, which makes the weight positive and the normal negative. What this means is that whenever you're writing out this equation, you're going to have weight minus normal equals mv squared over r. And if we take the mv squared over r to the other side and add the normal over, what our equation for the apparent weight begins to look like is that the normal is going to equal m times the quantity of g minus v squared over r. So I did the same thing where I switched weight into mg, I pulled the mv squared over r over, and then I factored out an m to get this. And we see that it looks very similar to the equation we have up here, but this is a g plus v squared over r. You're feeling heavier. Down here with this equation, you're going to feel lighter. Your stomach's all of a sudden going to be up in your throat, and you're going to feel very light. That's because we're subtracting this v squared over r from gravity. And remember that v squared over r is a centripetal acceleration, so we're allowed to subtract accelerations from each other like this, g being the acceleration due to gravity here on Earth. So both of these equations here, the going over a rise and going through the bottom of a dip, are very important for some traditional problems, and just thinking about, what's the minimum speed you need to get through a loop of a roller coaster? How fast do you actually have to travel in order to all of a sudden like hit this like a jump and just fall out here? So it's these kind of ways of thinking for a centripetal or a circular motion or circular force with this inward acting force here that we can start thinking about these kind of things. And it's pretty similar to what we did earlier in the year when we were talking about F equals ma, but now we're just thinking about it with a slightly different acceleration and a slightly way of different thinking about problems. And the big thing here is always remember, if you're going towards the center of your circle, you're positive. If you're going away from your circle, then that force is negative. So with that, these are finished. You can take it easy. Go try some of the practice problems now where you start looking at more Chick-fil-A stuff. And have a good one. Adios.